All right, so this lesson's on graphing reciprocal functions. So first things you need to know is reciprocal functions are a type of rational function, and then they're in the form of f of x equals a divided by x minus h plus k. So we are going to leave this rational function in this form, and it's really the only one we leave in this form. And the way you know if you have a rational function and you can leave it in this form are basically by its key features. And the key feature is the denominator has a linear function. So it's something of, mx plus b down there. And the denominator, the numerator is a constant, and k is just defined as a constant as well. So it just must be a positive or a negative constant. So if you're given a rational function in that type of form, it's called a reciprocal function, and you don't have to go ahead and combine the fractions to go through the work to do it. It's actually easier to leave it in this form. So those are the key features you want to look out for them in case you're given a mix-up of them. But let's go ahead and take a look at the parent function. All right, so let's go ahead and talk about what of these features are of this function. So a, the numerator. What you also have to be careful about is that, so a, when it's the absolute value of it is greater than 1, it's a stretch. So that means your graph will pull away from the parent values, and we'll discuss those parent values in a little bit. But so this a here, which you have to be careful about in a fraction, is this part here, if it's greater than 1, not a problem. The way you'll notice that the value is less than 1 is you have to look out for the values split between here and the coefficient of x, because that's the one where you know that you have a value less than 1, because in a fraction, a number less than 1 is written as a fraction, so the number will be also in the numerator and the denominator. Now, that doesn't mean it's always going to be less than 1 if it's that case. Like if you had a number that's a 3 up here and a 2 down here, obviously 3 over 2 is a number greater than 1. It would be a stretch. But I just wanted to discuss that with you to go back through that because there is a difference there. So when a is less than 1, you may see something like a 1 here and like a 2 here. So you'd have a 1/2 compression by a half. So just keep a lookout for that. The next thing is a, if negative, then it reflects across y equals k. And we'll have to talk about why we specifically have to talk about y equals k here. Yeah, so the next thing is the value of h. So this value of h here is your horizontal shift, which means it lets you know the parent graph whether it shifts left or whether it shifts right. Now, if you have x minus h, the graph will shift to the right, and if you have x plus h, it will shift to the left, all right? And that has to do with the fact of your zeros of the function, that inevitably if you actually put x minus a value here, when you find it 0, the 0 will actually become positive because you're going to have to add that negative to the other side. So that's why the negative shifts right and the positive shifts left. And then the vertical shift is exactly as it works, So if you have plus k, it shifts up. And if it has minus k, the graph will shift down. And then the other thing that's new to many of you will be this idea of a horizontal asymptote. And the horizontal asymptote is a value which is an undefined value. So it's a value that the graph can never actually define. It's a value that the function can never actually define, and it can't use it. So it's an undefined value. So you have an undefined value. So if the horizontal asymptote is a number that if you plug it in, it will make a error in the function. It will make it undefined. Whereas I wrote these backwards. Just realized that. Sorry, I just wrote these backwards. I just realized that. So that's not horizontal. I don't know why I did that. So this is your vertical asymptote, and this is your horizontal asymptote. Sorry about that. So your vertical asymptote is x minus h equals 0, and your horizontal asymptote is y equals k. So the vertical asymptote is literally a value for x, So if you plug this number in for x, what it does is it makes the denominator of your function, it makes it undefined. It makes it something that you can't do. Now the horizontal asymptote is actually y equals k. And the reason that is because you can never actually make this value. So we're just going to go through the parent function and write these things out, and then we'll go through it. But I do have one last thing here is asymptotes. Think of as a limit the function has as it approaches a value, but it can't actually create it. All right, so you're going to get closer and closer and closer to this number, but you're not actually going to use the number itself. All right, so let's go through the parent function. All right, so here's the parent function. The parent function is 1 over x. So we're going to go ahead and we're going to go through the steps of getting all this stuff labeled, and then we're going to graph it. So the first thing you want to always do for these ones is you want to figure out, all right, your a. So go through the steps of what is a. So a equals 1, so parent function, obviously no stretch or compression. All right, your h. So the h is what value are you adding or subtracting from x in the denominator, and that's 0. And then you get the value of k, so which function, what value am I adding out to the actual fraction, which in this case is 0. Now all those values are important because they tell me a couple things, all right? And the couple of things they now tell me are going to be, I have no shifts and I have no stretches or compressions, but they're also now going to tell me in the form of this problem, okay, that I have a vertical asymptote, okay, I have a vertical asymptote at x equals 0, all right, and I have a horizontal asymptote at y equals 0. So y equals k and k equals 0. So this is y equals 0. So now what I'm going to do is I'm going to set my graph up. I'm going to set my graph up here, and then I'm going to start plotting points around it. So the first thing I'm actually going to do is I'm going to graph my asymptotes. So my asymptotes are at x equals 0, so that's the vertical asymptote. So right along that y-axis. So hopefully you can see it here in red. And then the horizontal asymptote is at y equals 0. So basically now what I'm saying to you is I'm going to make a table of values, except I'm not going to include the x equaling 0, all right? The horizontal asymptote is important for graphing purposes, and we'll just go through that. So, all right, so the parent function. So let's just talk about this parent function. So let's make a table of values here. So we have x, and then we'll have f of x. So x and then f of x. So I'm going to plot my points in blue here. So if I plug in the value of, say, -2 into my function, I get 1 divided by -2, which is -1/2. And if I plug in, say, -1, all right, so using the values for x, I have -1, and I get the value of -1, because 1 divided by -1 is -1. And then I go to, let's just take a -1/2, all right, and if I plug in a -1/2, what you see is I get a -2. So the reason this is, again, called the reciprocal function, all right, so if you take a look at this parent function, all right, a lot of the answers are just the reciprocal of one another, which is where it got its original name. Now, it's harder to see once you start doing transformations and things like that, but the answers will be reciprocals of one another. So now we have to skip over 0. All right, so let's continue on with this, and I'm going to choose positive, not the negative. I wrote the negative again. So I'm going to choose +1/2, and 1/2, if I plug it in there, 1 divided by 1/2 is +2. And continuing my table off to the right here, that if I use +1, 1 divided by 1 is 1, and if I use +2, I get 1 divided by 2, which is 1/2. So then what I'm going to do is I'm just going to go ahead and plot these values, and then we're going to see what happens and what they look like. So -2 is at -1/2, -1 is at -1, and -1/2 is at -2. So it looks like, so what you see there, it looks like sort of a curve is starting to form. All right, and what that curve is doing, right, just so for instance, if I were to pick another number, say like -5, all right, 1 divided by -5, if you notice, is about 1/5. So what it's doing is it's kind of creating like a boundary. It should seem that way for you. Now, it doesn't always work that way because there are instances where you're able to cross over a horizontal asymptote You can never cross over a vertical asymptote, all right? But a horizontal asymptote, there are instances where you can cross over a horizontal asymptote. We aren't going to get in those examples in Algebra 2, but a vertical asymptote you can't ever cross. But for you, what it's going to feel like, okay, is that most of the stuff that you're going to graph, you'll never cross these asymptotes. So what you have here is you've got this side that looks like it's getting really, really close to this asymptote, but it can't ever actually cross it, and it doesn't actually ever get to it. So what we do is we draw arrowheads at the end, all right? So then we go on to the other side, and you get 1/2, and you get positive 2 there. You get 1 is at 1, and then 2 is at 1/2, and it's the same sort of deal here, all right? As it looks like it begins to curve here, okay? It looks like it's getting really close to that value, but it doesn't actually ever attain it because you can't plug a number in that allows you to do it. And the graph gets really, really close to y equaling 0, but it can't ever cross it. So this right here is what its parent function looks like. And what you want to get in the habit of is knowing that its distance and its relationship from where your asymptotes cross, all right? So it's always the parent function, if there's no stretches or compressions, is always 1 unit right, 1 unit up, 1 unit left, 1 unit down. So it kind of has this that thing there. That's what's going to help you determine from stretches or compressions, because these are the points, okay? So these points here that I'm going to highlight here in stars, these points right here, okay? Okay, these are the points you really want to remember. They're just how far they are from where the asymptotes intersect, because those are the values that you're going to use. So you're going to need 6 points when graphing these functions. All right. So I think the best point to do here would just be go through an example of this, but you kind of need to remember the parent function table in case you have a stretch or a compression, or you can just go ahead and plug numbers in and you could go that value as well. All right, so here we go. All right, so here's an example, okay? We have 2 divided by x plus 4 minus 7. So what I've got here is I've got that the value of a is equivalent to 2. I've got an h in this case, and my h is equal to 4, okay, plus 4, so that's going to be negative 4. And my k is going to be equal to negative 7. So how do I know that h equals negative 4? Well, I know that h equals negative 4 because this is a plus sign here, all right? So that means the h must be, okay, that is the actual value that you shift, all right? So I know I'm going to be shifting left 4. So I don't write just left 4, all right? I'm just writing that the h is negative 4, all right? So here, those values are important. So now what this allows me to do is it allows me to say this. It allows me to say my vertical asymptote, okay, is that x equals h. And so therefore it's x equals negative 4. And my horizontal asymptote, okay, is at y equals k. All right, so that means it's at y equals negative 7. So what I'm going to go ahead and do is I'm going to go ahead and graph those in. So in red, so you can see them, x equals negative 4. So here we go, and you draw it in, your asymptotes, sorry, I should have maybe mentioned this earlier, you draw in with a dashed line because that's a value that it can't equal. And then we go to negative 7, and we draw the horizontal, and notice here's where they intersect. So then from here, what I'm going to do is I'm going to go ahead and graph my points. Now, you can graph this based off of transformations if you want. So what you have here is you've got a vertical stretch. So if you want to go based upon vertical stretch, all right, what you can do is all of your points are going to have a relationship 2 times greater away from the point where your asymptotes cross. So normally you went over 1, down 1. Now I'm going to go over 1, down 2, if that makes sense. So it's twice the distance away. So then I go over to the one where I did a half. To do a half, I went left 2 units and down a half, but I have to double that. So doubling a half, you get 1. Okay. And then the other one was over a half, and I went down 2, but now I've got to go down 4. So now my graph doesn't really have it, but there's that. All right, so then the next thing I've got going on here is the next value on the other side. So over 1, but now up 2. And then it's going to be over 2, double that, right? So notice it's just going to be the reciprocal of the before, over half, but now I'm going to go up 4 in this case. So up 4 from it. Okay, and then what I'm going to do is I'm just going to go ahead and draw it in there. And what you'll see is I get a flattening effect, okay, around the curvature part. All right, but it is the same thing. So then there you go, and there's your example for you guys to work on for your notes. All right, sounds good.